Hello everyone, today I will talk about QuickUpdate, a real-time personalization system for large-scale recommendation models. This work was done when I was at Meta along with several of my colleagues at Meta. Recommendation models are widely used in many online companies. They are used across many online industries such as entertainment, e-commerce, social media and so on. For example, Netflix uses them for movie recommendations, Amazon and Alibaba use them for product recommendations, Meta and X use them for user feed recommendations. These recommendation systems consume a significant part of the AI compute cycles at Meta. They are used for important use cases such as generating ad recommendations or user feed recommendations. Now let us look at the deep learning recommendation architecture. Typically, these recommendation models consist of dense layers and sparse layers. Dense layers correspond to continuous or semi-continuous features such as age, income, etc. Sparse layers correspond to categorical features such as user ID, item ID, etc. These features are used in conjunction with embedding tables. Each category in a sparse feature may be mapped to a row in an embedding table. These embedding table sizes can be in order of terabytes and constitute more than 99% of the model size. Now let us look at the recommendation model training pipeline at Meta. It consists of data readers which collect the user activity, stores them and feed them to the trainer. The trainer trains the model using the data from the data readers. Trainer is a cluster of CPU nodes where each CPU node is connected to several GPUs. GPUs perform the model training. Dense layers are replicated across the GPUs as they are smaller in size. Sparse layers are distributed across the GPUs or CPUs as they are larger in size. Trainer publishes the model which is loaded onto the inference servers. Each inference server is a CPU node attached to several GPUs. In an inference server, the serving model is distributed across the CPUs and the GPUs. In online training, this recommendation model pipeline is continuously run. The model is continuously trained using the real-time data and the serving model is periodically refreshed to keep it fresh. Real-time updates to these online models can significantly improve the prediction accuracy. For example, when showing ads to users, if we can quickly update the recommendation model based on the current user activity, it can significantly improve the quality of ad recommendations. To measure the importance of real-time updates, we experimented with one of the widely used recommendation models at Meta. We compared the accuracy loss between a fully fresh model and the model that hasn't been updated for several hours. In this figure, x-axis shows the time period for which a model hasn't been updated and y-axis shows the accuracy loss when compared to the fully fresh model. At Meta, even a 0.01% accuracy loss is a significant loss. We can see that even with a 1 hour update latency, accuracy loss is greater than 0.01% and for a 7 hour update latency, it can go more than 0.6%. Now let us look at the challenges in frequently publishing the model from the trainer to the inference servers. One of the main challenges in frequently publishing is due to large embedding table sizes. As these embedding table sizes are in order of terabytes, publishing such large models very frequently is not possible at scale due to the limited network and storage bandwidth. To publish the models frequently, we investigated publishing only the updated model instead of the entire model. However, we can observe that a large percentage of embedding tables are updated within a short amount of training time. In the graph here, x-axis shows the training time, y-axis shows the percentage of model updated. We can see that within 10 minutes, more than 55% of the model is updated. So, updating the embedding tables frequently in a lossless manner is also not possible. Also, as model sizes are growing rapidly, we need a scalable solution to publish them from the trainer. One of the main techniques we use to reduce the embedding table update size and make frequent publishing feasible is to publish only the important updates. To select the important embedding table updates, we looked at two ways to prune the embedding tables. One, pruning the entire embedding tables. Second, pruning embedding table rows. We found that pruning the embedding table rows is results in higher accuracy while minimizing the update size. We use the optimizer state to prune the embedding rows. For an embedding row, optimizer state is the average squared sum of the historical gradients to it. So the rows with larger values of optimizer state indicate larger updates to them. We use the delta of the optimizer state between the previous publishing interval and the current publishing interval. Large delta optimizer state values indicate the embedding rows that have changed a lot in the current publishing interval. Intuitively, publishing the rows with a lot of recent activity may give more accuracy gains. As we frequently publish only a part of the model, the serving model may deviate a lot from the training model and may result in accuracy degradation. So, to keep the long-term accuracy of the model, we intermittently publish a full snapshot of the training model. However, the number of inference servers required is directly proportional to the size of the serving model. To significantly save the serving resources, when publishing the intermittent full snapshot, we prune the inactive embedding rows with optimizer state close to 0. We also quantize this pruned model to further reduce the size. This pruning and quantization of the full snapshot have negligible impact on the model accuracy. There can be an incompatibility between the intermittent full snapshot pruning and the selective pruning that we do when frequently publishing the update. A row that has been pruned during the full snapshot publishing may appear in the frequent update. These rows may lead to a lot of reshuffling of the serving model across the GPUs, as embedding tables are stored in compact array data structure distributed across the GPUs. To avoid the costly reshuffling, for frequent updates, we select the embedding row updates only from the rows that are not pruned during the full snapshot publishing. With this custom pruning scheme, the size of the embedding tables in the serving model remains the same. So, we can avoid this costly reshuffling. We compared the accuracy of this custom pruning scheme with the row selection scheme that has no constraints on which rows to select. We found the accuracy difference to be negligible. Now, we will look at the challenges in updating the serving models. To atomically update the serving models and see a consistent view of the update, we may require a buffer node along with the currently serving node. However, this increases the serving infrastructure. So, we explore directly patching the frequent updates onto the currently serving model to avoid using the buffer nodes. When directly patching the updates, inference queries may not observe consistent view between the updates. However, we observe accuracy gains during patching the update when compared to the stale model that hasn't received any updates. So, serving a subset of fresh rows leads to accuracy gains. Now, we will look at the quick update workflow. The model is trained across the GPUs using the real-time data. The training happens in intervals, and at the end of the interval, GPU training is paused and the model state is copied onto the CPU attached to the GPU. After copying the model to the GPU will continue training. CPU has larger memory to hold the model copy and process them. Initially, CPU does full snapshot pruning on the model copy and then quantizes it and publishes the full snapshot. Again, at the end of next interval, model state is copied to CPU from GPU. CPU then applies custom selective pruning, quantization, and publishes the frequent update, which is directly patched onto the serving model. This publishing of frequent updates continues for next several intervals. To keep the serving model close to the trainer model and avoid accuracy degradation in the long term, a full snapshot is published again. And this cycle of publishing partial and intermittent full snapshot continues. Now, let us look at evaluation. We evaluate quick update on one of the largest recommendation models deployed in Meta using real world data. Here is a chart showing the accuracy gains for several update sizes when compared to stale model. X-axis shows the training period and y-axis shows the accuracy gains over the stale baseline model that hasn't been updated during the training process. We can see that for all the update sizes, the accuracy gains increase over time. We compared the accuracy loss for several update sizes when compared to an ideal fully fresh serving model. Ideal fully fresh serving model is the current model at the trainer. X-axis shows the training interval and y-axis shows the accuracy loss with respect to a fully fresh baseline model. We can see from the chart that higher update percentages have lower accuracy loss. With a 10% update size, even after 10 hours, the accuracy loss is less than 0.01%. We can postpone the intermittent full full model update by at least 10 hours with a 10% update size. With a 5% update size, we can postpone the intermittent full model update by 6 hours. Now, we will look at the bandwidth savings when publishing the model from the trainer to the inference servers. In QuickUpdate, the amount of bandwidth usage depends on the model update size, update interval, and frequency of the intermittent full update. In this chart, x-axis shows the training hour and y-axis shows the update size in percentage of the model for several scenarios. Baseline scenario is a full model updated every hour. This baseline writes 100% model size every hour. With update of 5% model size for a 10-minute interval and intermittent full update for every 6 hours, it writes on average 43.6% model update every hour. With update of 10% model size for a 10-minute interval and intermittent full update for every 10 hours, it writes on average 68.2% model every hour. With 5% update size, we can get an accuracy gain comparable to a full model updated every 10 minutes. A full model updated every 10 minutes would write 600% of the model every hour. In conclusion, with QuickUpdate system, we enable online training with a serving accuracy that is comparable to a fully fresh model. It utilizes 13x lesser bandwidth compared to a frequent full model update while providing an accuracy comparable to it. To achieve this, we made use of several techniques such as frequently publishing partial updates combined with intermittent full model updates, directly patching the updates at the inference servers, and so on. Now I am happy to take any questions that you have.